Yeah. Let us start today's webinar. Respected senior INS members and friends, on behalf of INS and on behalf of INS Webinar Committee, I welcome you all to this 24th webinar in this series. Through this fortnightly program, the subcommittee is bringing to the knowledge and information to the INS members about recent developments and accomplishments in different fields of science and technology. In the previous programs, we have covered topics on climate change, renewable program, renewable energy, mathematics as science, healthcare, science and societal issues, and others. Large number of viewers have participated online and also offline through our website. Many have reported to have been greatly benefited by the webinar information available in our website. This is true for the viewers from DAE family and outside the DAE family. Encouraged by this positive response, we invite eminent speakers, executives, and industry leaders to give talk on our Zoom platform. Today, I am happy that Dr. Kiran Kumar, former chairman ISRO, has agreed to give a talk to us, and the topic is harnessing space technology. Sir, I am delighted, and I welcome you on behalf of INS and on my own behalf to this online INS program. We are greatly honored, and we are fortunate to listen to you today. Friends, as you may know, only 2 days back, ISRO launched its 55th mission named as PSLV C-53 from Sriharikota, putting 3 satellites for Singapore. The technological spin-off, this is very important and thrilling when I read it. The technological spin-off in this mission is utilization of the spent upper stage, it is called PS4, as a stabilization platform for scientific payload. You know, the last portion of the launch, which is a junk in the space, that junk is utilized for doing scientific experiments. So they call this as a poem. This is called poem, where space experiments will be performed for many, many years. On 14th February, PSLV C-52 was launched, thus injecting 3 satellites in the Sun synchronization polar orbit, that is at 529 kilometers up in the space. On 20th February 2022, PSLV C-51 was launched after putting payload of Brazil and 18 small satellites. So in all, in the history, ISRO has placed about 342 satellites in the orbit for 34 countries. This is itself a magnificent achievement, which will give us a lot of pride as an Indian. They have planned Chandrayaan, Gaganyaan, Lupex, Aditya L1, Reset, Nisar, Mangalyaan, Shukrayaan, and many more. Importantly, ISRO has also launched India's own GPS, which is officially called Navik. So India can now, we don't have to depend on other GPS. We have our own GPS now made by ISRO. ISRO has also set up a center for training astronauts in Chalikere in Karnataka. Recently, ISRO chairman in June 2022 opened the production facility of large private spacecraft manufacturing facility. So these are all some of the space technologies that we know, but Dr. Kiran Kumar, I'm sure, will be talking more when he will speak on harnessing space technology to us. So, sir, I welcome you once again. Now I request our INS Secretary C.S.K. Malhotra to formally welcome the speaker. And then I will request Dr. Ramanamurthy to introduce the speaker to the audience. Malhotra ji.
Thank you, Dr. Ramarao. Good evening, everyone present on the forum. And a special welcome to Dr. A.S. Kiran Kumar, the former Secretary, Department of Space and former Chairman, ISRO. And whenever, we are very proud that we belong to Department of Atomic Energy, and we are prouder that along with the Department of Atomic Energy. I mean, just like our own, I would say, I would prefer to call baby brother, younger brother, ISRO. We are equally proud of their achievements. Every time they achieve something, I think, as Modi ji says, our chest becomes 56 centimeters every time ISRO achieves something. So Dr. Ramarao was just mentioning about the successful mission 3 days back. I only remember, I will not repeat what Dr. Ramarao said. I will only say it in the form of the very old quote by Dr. Homi Jahangir Bhabha, while arguing for the case of atomic energy, and which included, I think, when he was speaking in those days in 1944, when he was saying atomic energy, probably somewhere he meant space technology also. So whenever he used to say atomic energy, within brackets, space technology is included. So he had made a statement while putting the case for opening a center, basically TIFR, to Tata Trust, Sir Dorabji Tata Trust. He had argued that, moreover, in a few decades from now, we will have experts within our country, and we will not have to look to the world for these experts. So I think it definitely, I always give this quotation telling that it has come very, very, very true in case of Department of Atomic Energy, and very proudly I say it has become even more true in case of ISRO, where we have not restricted ourselves. The Department of Space and Department of Atomic Energy, we have not restricted ourselves to what Baba said. We have got beyond that. Now we are providing experts and expertise to the rest of the world from within India. And that's an example that, as Dr. Ramarao mentioned, that the launch, the PSLV launch, recent one, was not for the country. It was for Singapore. We have launched some things. So with those words, I extend a very warm welcome to Dr. Kiran Kumar and to all the audience present in INS, all the seniors. Usually this welcoming job is done by our respected President, Dr. S.K. Mehta. Today he is not in the best of his health. So he expressed inability to do that. So I have welcomed all of you. So once again, I welcome all of you. And I wish that this 24th webinar will be a great success. Thank you very much. Look ahead for the evening. Yes, Ramarao-ji, you can go ahead.
Shall I take on?
Please, Ramanamurthy.
Yeah. So good evening, and I join the others in welcoming Dr. Aluru Selin Kiran Kumar, an eminent Indian space scientist and former chairman of ISRO. It's my privilege to introduce him to the forum. Dr. Kiran Kumar graduated in physics honors in 1971 from the National College, Bangalore University, followed by post-graduation in electronics in 1973 from the same university. He went on to complete his MTech in physical engineering in 1975 from the Indian Institute of Science, Bangalore. He started his career in ISRO by joining Space Application Center, Ahmedabad in 1975, working on spaceborne electro-optical imaging instruments. He rose to the post of the Director SAC in 2012. He was Secretary, Department of Space, Chairman, Space Commissioner and Chairman, ISRO from Jan 14, 2015 to Jan 14, 2018. Dr. Kiran Kumar is credited with the design and development of the electro-optical image sensors used in India's first remote sensing satellite Bhaskara, launched in 1979, and the subsequent one in 1981, as well as the ocean color instruments used in weather forecasting, sea zone landscape mapping, and telecommunications. He has also contributed to the design and development of the imaging instruments for projects such as INSAT 3D, ResourceSat, Microsatellite, and Cartosat. He has been associated with the development of 3 of the 5 scientific instruments aboard the Chandrayaan-1 and Mangalyaan spacecrafts, such as the terrain mapping camera and hyperspectral imager. He has represented Indian Space Research Organization at many international forums, such as the World Meteorological Organization and the Indo-US Joint Working Group on Civil Space Cooperation, and was holding the chair of ISRO at the Committee on Earth Observation Satellites. He has delivered numerous lectures and keynote addresses in seminars and conferences on space science. He has also published more than 40 articles in peer-reviewed international journals. Dr. Kiran Kumar is the recipient of many awards and honors, such as the Indian Society of Remote Sensing Award in 1994, the Wasvik Award in 1998, the Astronautical Society of India Award in 2001, the ISRO Individual Service Award in 2006, the Bhaskara Award of the Indian Society of Remote Sensing in 2007, the Team Achievement Award of International Academy of Astronautics in 2008 for Cartosat and 2013 for Chandrayaan-1, the ISRO Performance Award from the Indian Space Research Organization in 2008, the Vigyan Ratna H.K. Firodia Award in 2017 for his direction of Indian space programs in various areas, and the highest civilian award for France for his contribution to Indo-France space cooperation. He is also the proud recipient of Padma Shri from the Government of India in 2014. He was awarded honorary doctorate from Geetam University on 24th March 2015. He is a fellow of the National Academy of Engineers and is a corresponding member of the International Academy of Astronautics. He is currently the chairman of Bangalore Association of Science Education, which is known as BASE, which administers the Jawaharlal Nehru Planetarium, Bangalore, and also the president of the Aeronautical Society of India. So with this introduction, now it's my honor and privilege to hand over the floor to Dr. Kiran Kumar. Sir, it's you may please commence your presentation. Welcome once again.
Thank you very much for this introduction and also this opportunity to be part of this program, where I'll be talking about what India has done in the space program. Just take you through the journey. I hope you are able to see the presentation now. Are you seeing?
Yeah, the poster is the first slide. Is it correct, sir?
Yeah, correct. So you're seeing that, right?
Okay. Yeah.
All right. Okay. So at the outset, I should like to thank the Nuclear Society for giving me an opportunity. And as was pointed out, that actually the space program took birth from the nuclear energy program, and Dr. Homi Bhabha and Dr. Sarabhai are the two stalwarts who actually thought of making use of the space technology for country's benefit. And it's indeed a great opportunity to speak to many of you and probably remind you of the kind of work that ISRO has done starting from the early period till now, and also bring up in the course how India has been able to take advantage of this disruptive technology of space technology which came up in the early 50s. And as many of you are quite familiar, it's Dr. Sarabhai who was looking at how our national goals involve leapfrogging from a state of economic backwardness and social disabilities, attempting to achieve in a few decades a change which has historically taken centuries in other lands. And of course, Dr. Sarabhai's centenary year was celebrated last couple of years, and then during the course of this, we did actually conduct many programs reminding us of what he did. And as you can see, early in the 50s, when the first object went into space, which was put in by Russians, it was the ability of people like Dr. Homi Bhabha and Dr. Sarabhai to convince the people who matter that India should actually get into the process of doing some work in space technology. And it's only through that we can make a difference to the progress in the country. And within about 6 years of launch of the first object, India was able to do on 23rd of November 1963 a launch from Sriharikota. Probably at this point, it was Dr. Sarabhai's effort of convincing his friends from Germany, France, America, and Russia, showcasing to them that we have a unique place in Thumba, an equatorial geomagnetic equator being very close to Thumba, and conducting upper atmospheric research there can be beneficial for the global scientific community. And with this in mind, bringing sounding rockets in the form of kits, getting them assembled. And this was, of course, assembled in the church, what you see in this photograph. We will see some more details in subsequent slides. And starting from this humble beginning of assembling sounding rockets is how India started its program. And at that time, not only in terms of launch vehicle, it was also, we had many other scientists who were actually trying to borrow the technology and technological components from their friends abroad. For example, Dr. Pisharuti conducted a very unique experiment called coconut root wilt disease experiment, which was for the coconut plantation, by borrowing a Hasselblad camera from NASA laboratory, flying it on an aircraft, and using that, showcasing how remote sensing can be beneficial, was demonstrated in 71. And similarly, a balloon experiment for looking at the agricultural outputs of rice and other crops, that was experiments were done. And initially, of course, one of the very important experiments that were conducted was way back in 1975, an experiment called SITE, Satellite Instructional Television Experiment. And this, of course, was the real, you can say, a trailblazer, not only for our country, but also for all the developing nations, because with his vision, he could, Dr. Sarabhai could convince Americans that they should allow us to borrow their advanced technology satellite and move it over to the Indian longitude, and for about 1 year conduct experiments. And you can imagine at that time, only the 4 metros had the privilege of looking at the broadcasting service. And at that time, 2,400 remote villages of our country, and almost benefiting 2 lakh people and 50,000 primary school science teachers. And what was done in that was at SAC Ahmedabad, equivalent to today's direct-to-home television, the experiment, the set-top, what we see as a set-top box today, was almost like a half a rack equipment. And that was realized, and using the black and white television developed at ECIL was used, and a 3-meter chicken mesh antenna was used, and demonstrated that the satellite is the way to go about for reaching to the entire community in the country. And this particular experiment was also actually got at that time the Marconi Award as the world's largest socio-technological experiment conducted to demonstrate the benefits of space broadcasting. And at that time, ISRO did work along with the Ministry of Education and NCERT and many others. And as you can imagine, creating content for this program was also important. And all these activities were being done at Space Application Center, Ahmedabad. And for about a year, this program, and of course, we can also easily appreciate if you go and tell the Prime Minister in the 70s that what you are going to speak can be heard across the country, you don't require too much of a convincing for getting the program approved. That's how the INSAT program, communication program, got approved. And then, of course, INSAT did one more thing, not only broadcasting, it was also looking at the cloud pictures from space and using that, enabling, following the cloud motion vector and weather forecasting information, gradually developing, starting with INSAT 1 series, which had only 2 channels. You were able to look at India and surrounding India in the visible and water vapor thermal infrared channel, 2 channels with 11 kilometer for thermal infrared and 2.75 kilometer resolution for visible. Starting with 2 channels and 4 images per day, today we have gradually grown to 48 images per day every 15 minutes, and then covering in 6 different wavelengths: 1 kilometer visible, shortwave infrared, mid-wave infrared, water vapor, thermal infrared, and also using an instrument called sounder, generating vertical temperature and humidity profile. And all this information goes into the weather forecasting model of IMD, and almost 30 to 48 products every 15-minute interval is actually generated and goes into the database of the various systems. And today we have 2 satellites providing this information, what we call 3D and 3D repeat. And using this every 15 minutes, you get the complete coverage of India and subcontinent. And using all this information, today, one of the key things that has happened is the tropical cyclone monitoring and prediction, which has become a very important aspect. In the earlier decades, cyclones used to cause, super cyclone used to cause loss of life in tens of thousands. But now, as the ability to predict the landfall and also the time error of at what time the cyclone hits a particular location, both of them with a significant improvement, being able to tell the disaster relief agency almost days in advance. They're able to evacuate the people and save thousands of lives. And in the past decade, the number of deaths that have occurred in the presence of super cyclone is come down to single-digit numbers. And not only that, the amount of money and the resources that is required to be spent for this saving also is continuously improving. And over last 3 to 4 decades, the improvement has come because of the satellite capability. And this slide just shows what kind of improvement has happened in both in terms of the track error and the landfall time error. And not only this, today there is also the possibility of identifying the flooding zone and up to what depth, at what region actually the waves which come as a result of this cyclone affect the land. And as a result of that, the disaster relief agency is able to move ahead and go further. And other important experiment was the satellite, satellite instructional television experiment, which we started INSAT series. And again, the very important thing at this point was in the early 80s, no single satellite had the capability of providing broadcasting, communication, and weather monitoring in a single platform. And ISRO had to conceive of this particular satellite because of the resource restrictions and inability to afford 3 independent launchers and 3 independent satellites. So all 3 were actually put in one, and this was known as a 3-in-1 satellite. And since the first generation could not be realized in the country, it was realized through an American company, Ford Aerospace. But from INSAT 2 onwards, from 1992, all the satellites, communication satellites, have been built indigenously. And today we have a large number of communication satellites which have grown from few bands like C band, S band. Today you have KU, KA, and not only that, you have broadband capability, and very soon you will have 100 Gbps high throughput satellite with multi-beam satellites providing, and a large number of such constellation actually is enabling providing not only DTH service, but also the broadcasting and also for the security as well as for the ATM services and stock exchange related activities, all of them. And during the course of these decades, ISRO also was able to showcase how the space technology based resources of telemedicine and teleeducation could make a difference. This was much before the terrestrial communication activities grew, and then today, of course, terrestrial communication has overtaken much of space-based communication in the area of telemedicine and teleeducation. And also the recent COVID also has demonstrated how this digital communication capability is making a huge difference. But notwithstanding this, starting of these concept of linking places like Andaman and Nicobar and remote places to super specialty hospitals, and even today linking unreachable areas to super specialty hospitals, and also the primary schools and secondary schools, linking them, providing virtual classrooms for activities that were done. And in addition to that, of course, navigation area also, what we were able to demonstrate is look at a mechanism where Indian subcontinent was actually, so you can say, sort of a hole in the global communication network of navigation, where aircrafts fitted with the satellite-based receiving system were not supported in our region with the GPS facility, but by setting up what we call as Gagan, that is GPS-aided geo-augmented navigation system, where Airports Authority of India worked along with ISRO, and by measuring the signal strength in about 26 locations and uplinking it and transmitting via our transponders, ground receivers are able to provide safety of life and integrity assured signal to the aircraft instruments. And probably you would have seen in the recent weeks, both Indigo as well as SpiceJet has started using this service, not only for en route planning, but also for landing in some of the remote airports where the instrument landing system is not available. Making use of this GPS service, they're able to do the landing. And India has become one of the first countries to adopt them for less, you can say, instrumented airports. And this particular capability is also a significant development. And also the government of India has actually made it mandatory for all aircrafts registered in India beyond 2019 January to carry this Gagan enabled receiver system, so that they can use it for their both en route planning as well as for landing. And of course, the other important thing was providing an indigenous constellation system of NAVIC, where unlike Americans, Russians, and the European and Chinese, who went for a global navigation system requiring a constellation between 24 to 32 satellites, we went for a regional navigation, which required only 7 satellites operating in geostationary and geosynchronous platform. And using this today, a large number of services have started becoming operational. We will see some of those results in some subsequent slides. And today, the Airports Authority of India has actually enabled operational use of this for aviation, safety of life, and increased efficiency, and for civilian application and for surveying. And not only that, NAVIC has also provided the timing service required for power synchronization across the power stations and for all tracking related activities. For all this, almost about 15 ground stations across the country has been set up, which receives the signals from all these satellites. And by making measurements locally at these stations, they determine the ionospheric delays and ionospheric errors. And using this information, the data is put back into the satellite for the ground receivers to improve on their ability to locate in terms of latitude, longitude, and timing. Another very interesting story which got actually developed when Dr. Sarabhai had to conduct the first experiment in Thumba of launching the sounding rockets. He had to actually make use of the services of the bishop to convince the fishermen in that beach to explain to them that if you vacate this place today, the country will benefit in terms of the activities and the research that happens. And for this, he had to actually get the services of this bishop and convince the fishermen. Just as though to demonstrate what had been told, from 1999 onwards, India was able to provide to the fishermen specific information about where to go for fishing by determining the prospective fishing zone. And for this, using our satellites and looking at the color of the ocean in 8 different wavelengths and using them, identifying the chlorophyll and chlorophyll map and thermal fronts, it was possible to locate through the food chain of the fish, where exactly the fishermen need to go for assured catch of fish. And initially this service was started with a center in Hyderabad called Indian National Center for Ocean Information System, which was part of the Ministry of Earth Sciences. And initially it was a Department of Ocean Development. And initially this was provided through pager system and also through the actually telex messages going to the Fishermen's Association, getting it displayed at local places. But then today with our Navig, what has happened is a small gadget which is actually receiving the signal from Navig locates itself when the fisherman is in the ocean. It gives him the specific location, and Navig also has a messaging service through which the prospective fishing zone latitude and longitude is also broadcasted, and the gadget, which is battery operated and communicates with the handheld mobile in the hands of the fisherman. Mobile itself does not require any connectivity to the terrestrial tower, because you can easily imagine that the mobiles, once they get into the ocean, will not have any terrestrial connectivity. But then connecting with Bluetooth and Wi-Fi, it is able to communicate with the gadget, and there's an app on the mobile which converts this information into a video compass and points the direction to which the fisherman has to go for the catching the fish. Not only that, in his mother tongue, it tells him about any weather vagaries that could occur in the coming days. And also if he is approaching international boundaries, it alerts him. So all this is happening on his mobile in his mother tongue and video compass mode. So here you can see the example of a person who does not know reading or writing, taking the use of the most advanced technology of launch vehicle, satellite application, and a mobile in his hands, providing him with service. And these kinds of gadgets are being provided by the state governments to the fishermen community as a part of the government's support to the fishermen. And the almost 7,500 kilometer long coastline with lakhs of fishermen in the coastal area are getting the benefit of this particular area, this particular activity. The specific survey which was done has also shown that there is an increased fish catch, reduced the time of search for the fishermen, and this also saves in terms of fuel, petrol and diesel, almost tens of thousand crores a year because of these activities. Then today the Navig-based service is also used by railways, not only for various communication, but also for railway information tracking system, and also enabling the efficient use of location of the railways at the service places, and also providing this information to the general public. So this has a lot of demonstration has happened now. Rajdhani has started using, and in the coming years, this is going to be a fully operational system where not only remote unmanned level crossings are being supported with this kind of development that have happened in communication and navigation. For doing all these activities, the various kinds of developments that were needed was, of course, in terms of imaging system, starting with the Bhaskara satellite, when we started with a 1 kilometer resolution, 340 kilometer by 340 kilometer frame imager, and from that gradually building up the capacity. Today we have 30 centimeter imaging. We're providing very high resolution capability, and not only in single wavelength but also a large number of different wavelengths and different spatial resolution, temporal resolution, and also spectral resolutions. Using all this, the data is being provided for a host of activities. and some of the innovative solutions that were adopted, we were among the first to adopt a CCD technology, which enabled not only like ocean color sensor and also Cartosat series of satellites being built. Our designs were specifically meant for meeting the requirements of our agricultural practices of small land holdings, and then generating information both for the phenological studies and also for specific high resolution information. And using this and hyperspectral imaging, again, as you can imagine, that if you are able to get finer and finer spectral resolution information, not only you can get the crop pests and also crop discrimination and the kind of fertilizers required for that. Here also gradually the technology has been built, and now we have a hyperspectral imaging sensor which is operating from space. And not only in visible, infrared and ultraviolet, we have also developed technologies. As you can easily visualize, the India, because of the June to September, cloud cover is going to hinder both visible and infrared observation. But microwave can penetrate through the clouds, and a set of instruments which are operating in microwave region, whether it's a scatterometer. A scatterometer provides the ocean wind vector information, and this data goes into the numerical weather forecasting model, not only of India, but also of the entire global weather forecasting community. And this information is provided within 3 hours of acquisition to the global community. And a C-band synthetic aperture radar, which can provide information about rice and jute and many other crop types, and multipolarization capabilities there. Not only these frequencies, but also in X-band, operating in low inclination and as a constellation, providing very high resolution information for strategic application. Also is these techniques have been developed and they are operating. And in addition to that, we also had a digital elevation model information, which was generated using an along track stereo imaging system, where we were able to generate not only for India, but also for all the surrounding region, for the entire globe, in fact, for providing digital elevation model using this data. And not only the space-based instrumentation, but also a large number of ground instrumentation, which was required, as you also would have seen, for making sure both in terms of corroborating and calibrating and also validating, you require a large number of in situ observations. And we did develop many of these radars, as well as automatic weather stations and multiple systems operating at different regions and providing the data to the various communities for such. Today, with the space technology inputs of digital elevation model being available, optical, microwave, and various wavelength data are coming from space-based instrumentation and navigation-based location information and mobile data collected through mobiles or other devices. All this data going into a suite of applications using computer systems and software is being adopted for socio-economic security, sustainable development, and disaster monitoring, as well as governance related activity. And another very important aspect, which again the Department of Nuclear Energy also has seen this happening, while you develop a new technology, making this technology useful to the user and then making them aware and accept usage of that is also a non-trivial job. And then, as you can easily imagine, when you go and tell somebody what they are doing on a regular basis, they can do better or in a different manner with a new technology. It requires a lot of convincing. And here again is an example. While space technology input started becoming available, different departments started accepting it and using it with their own time scales. Forest Survey of India started using in 87, Ministry of Earth Sciences Potential Fishing Zone in 99, and Airports Authority of India from 2003, IMD, though it was taking the onboard data from space, it was using its own ground-based observation processing system till 2008 for converting the space-based input, going into numerical weather models, and then Ministry of Agriculture for doing crop forecasting, etc. So all this took a lot of time and effort. And then one of the very important development that happened is forecasting agricultural output crops with a consistent decades of effort. The Mahalanobis Crop Forecasting Center was established in Delhi by Ministry of Earth, Environmental and Forest and Agriculture. And in fact, the current Prime Minister, as soon as he took over, he was using the extensively the space-based communication and remote sensing data when he was in Gujarat, along with the Bhaskaracharya Institute of Geospatial Studies. So we conducted in Delhi a program where almost more than 1,000 state and central government secretaries, joint secretaries, they were all brought together. And on that particular day, Honorable Prime Minister himself spoke extempore and explained to the secretaries how they can make use of space-based technology in their activities of their departments. And subsequent to that, the activity got a big fillip, and large number of ministries has set up space technology cells and expert groups, and the information generated from that is being disseminated in the form of geospatial technology through various platforms, whether it is Bowen or MOSDAC. These are all platforms where the data collected from the space-based, not only our own sources, but also collaborative agencies across the globe, providing this information to the different government departments and the public. They're all being done. And this just gives you a quickly in a glance the kind of application that has happened with the emphasis given by the government on various activities of space-based inputs. One of the things that happened during that time is enabling the master plan for 4,000 towns, and then site management plan for heritage sites, and then asset mapping for all, bringing all post offices, etc. And Manrega is another very important. I'll cover it in one of the subsequent slides. What is regularly happening is, based on the data collected over last many decades, land use, land cover maps are generated on a regular basis. 16 cycles of data is provided. These atlases are available for various usages and forms the backbone for many of the planning activities of the various government departments. And in the earlier periods, this was also used for identifying specific locations where one could drill the bore wells. More than 4 lakh bore wells were drilled using these specific data sets that were generated. Progressively, as the capability is improving, the resolution at which these activities are being done is improving, and also a signature for mineral mapping, etc. is going on. And geospatial support for governance, when you look at integrated watershed management, and then for Amrut cities, that is using geospatial database. Manrega as one of the things where it has made a significant impact. See, earlier, while what was going on across the various places, there was no good record of what was happening, and also accountability using these geospatial technologies. Today, more than 4 crore assets have gone into the database, and government departments have started making use of this for not only validating and also clearing and even payments, but they're also using it for planning activities, and not only for crop horticulture, crop insurance, crop intensification, a host of them. These activities are going on, and it has made a significant impact. And National Hydrology Project here also providing the daily evaporation flux, and then national weather based, vegetation based indices, rainfall information. All of this comes into the database, and more state governments have started adopting these techniques and going ahead. And these are some examples of how microwave-based data also helps in identifying the flood-affected regions. In fact, even for locust surveillance using space-based inputs and using models, identify which are the areas which they could be affected by locust is one of the things. And the space-based input for decentralized planning is where actually the panchayats, the elected representatives of the village panchayats are provided information in their mother tongue about the happenings not only in their place but also in their surrounding areas. Of course, here it is a lot of work. Work is in progress. Some places it has happened, in other places the continuing effort is going on for bringing it into practice, and various layers of data which is generated. This is made at the block level. Some states have adopted and gone ahead, and Rajasthan is one of the governments where they have moved very quickly and moved ahead. And even during the COVID times, using this geospatial capability was effectively used. And not only that, in a way, the COVID provided an extremely good opportunity for many researchers to study what happens when anthropogenic inputs or man-made pollution effects were very little, and a lot of studies came out of this, the atmospheric optical depth or particulate matter, what was the impact of anthropogenic activities or non-activities during that period. And then for blue economy and then coastal zone information, not only that, you can also imagine that a consistent data set of many years can be used for doing change studies. And this also National Information System for Climate and Environment Studies, the data is provided using not only our data, but also data collected from other space agencies. While doing all this, India not only worked on its own, but it also worked along with other space agencies. One example was Megatropics, where working with French government, we were able to provide a platform for microwave satellite instrument, which could provide radiation scanning as well as the specific information about humidity and temperature profiles. Using microwave data, this was being provided to the India Meteorology Department and also to the International Forum. Saral is another thing where of the advanced radar, Ka-band and radar altimeter, this data was being provided. And true to our traditional the concept of providing your own capabilities to the neighboring countries, India provided to the SAARC region free transponders, which today is effectively used by some of them. Bhutan and others have started adopting it slowly, but then the country used this also as a space diplomacy to provide. And one other very interesting development in a way you should think of is that you get recognized only when you are showing what you are capable of. While we made use of the American help, took American help during the initial period, the Americans did not do any common program with India until Chandrayaan demonstrated the Chandrayaan mission, and also later our own radar missions demonstrated the capability. Today we are working with NASA on a program called NISR, NASA ISRO Synthetic Aperture Radar, which one of the key things that was there, that is there using this, is you will be able to generate over the entire globe surface deformation to the tune of few centimeters and millimeters, which is going to provide very important input for future earthquake prediction activity. Not only that, this can provide information for a large number of our biomass and other important activities for us. There are two frequencies in which this data is generated, L and S band, and L band complete system is developed by the Americans, and S band component of that we are providing. And this is going to be, actually originally plan was 21, and now probably in late early 23 this will happen. And here again, the we borrowed from American hyperspectral instrument and flew on our aircrafts for generating ground information. But this time, our L&S airborne instrument is being flown by the American aircrafts in North America to generate the data which is going to simulate the S-band NISR data for the various future studies. So these are some examples of data collected by that L and S-band SAR data, and this has also been flown over a number of North American countries, and this data is being provided. So we built the capacity of putting satellites around Earth, low Earth orbit, geo-platform, then Moon and Mars are all the natural follow-on for moving. And for this, a host of different orbits were required to be done. And again, making use of the limited resources and limited capability as a reason for more bigger and bigger innovation, both the Chandrayaan mission as well as the Mars mission, we found ways of actually taking advantage of even Moon's gravity in planning these orbits and moving ahead. And space science program and advancing it was actually at the base of all the opportunities that came when you are putting the space-based system launch vehicles you are developing, starting from sounding rockets, even the Aryabhatta, which was the first satellite. We had gamma ray burst experiment and X-ray payloads, which were flown on that. And gradually the capability has been increasing, and Chandrayaan-1, we'll see some details of this. And in this lunar exploration, of course, Chandrayaan-1, when it was done, it was an example of how international cooperation can make a difference. And Chandrayaan-1, as you are aware, became a landmark because it demonstrated, and it, to the credit of discovering the presence of water on Moon, goes to this satellite. And then the Planetary mission, Mars mission, which was done, is again a very innovative way of taking advantage of the limitations what you have and coming up with a specific satellite which did in a maiden attempt. Chandrayaan-1 also not only demonstrated the presence of water, but it also changed significantly the thoughts about the Moon itself in many ways. For example, it was considered as geologically dead for a long time, but then data from this showed that dynamic and volcanical activity up to a few million years back was happening, and then complete absorption of impinging solar wind protons by lunar regolith. So like that, it made an impact. And Mars orbiter mission, of course, generated a larger number of full disk images of Mars. That was because we could not put it into a circular orbit at a lower altitude. Our orbits was going up to 80,000 kilometers. And as a result of that, we were taking advantage of that and providing. In fact, AstroSat mission is another very interesting mission where we were able to enable a large number of academic institutions and through them build payloads, and these payloads are operating, and the satellite is providing as an observatory, and researchers can actually task the satellite, ask for observation of a particular region and collect data. So they get the virgin data before others. And in this, the ultraviolet imaging telescope, you will be happy to know, actually has the highest angular resolution imaging capability in ultraviolet region. And it is also the most sensitive telescope until, for example, the James Webb came, and even it had better capability than the Hubble in this particular wavelength region. And as a result of that, our friends at IUCA are able to make observation of a specific region, what is called as AUD FS01, and collected data in the FUV photons, which was detected for the first time. And in Chandrayaan-2, we moved ahead of whatever instruments that were built in Chandrayaan-1. Many of them came from our friends from JPL and APL. For example, the surface water came from Moon Mineralogy Mapper. But in this, we built our own infrared imaging the instrument, which goes up to 5 microns and then dual frequency SAR, and we also have a instrument called class, which is again a very high resolution instrument, and then both topography measurements are possible. And L and S band SAR is providing very significant inputs to permanently shadowed regions, and this also helps because it also has polarization measurement. It is able to distinguish and generate unambiguous detection of both water ice and then dry ice and those information. These are just, we also have a very high resolution imaging instrument operating in Chandrayaan-1, which can provide almost like you can even see the boulders and small things on moon surface. And these are of course some craters which have been imaged. And this again an instrument which I was talking about. This particular instrument is one of the very advanced instrument, you can say, operating in planetary platforms. And this is able to generate, because it has got up to 5 microns water absorption band, just around 3.1, 3.2 microns. And it's able to show the absorption depth in a much more clearer manner than the previous instrument. And large number of these studies are going on. And this data is available in our what is called as ISSDC, International Space Science Data Center, which is accessible to researchers both within the country and across. So by now, for doing all this, the various missions that have been done, 53 successful flights of PSLV with the what was mentioned just a couple of days back, what was launched, and then with our own cryo engine, GSLV Mark II, Mark III, and then almost about 345 satellites of 34 countries. All this has been possible using this. And PSLV, starting from 1994, progressively this capability was being enhanced with each time this launch vehicle built in a new capability. And today we used it not only for satellite recovery experiment, and it also happened to be the first non-cryo engine which launched a geostationary transfer satellite, Kalpana 1, and then later Chandrayaan, Mars, and then 104 satellite which was put in 2014 also happened to be at that point of time one of the last, it was sort of a record at that point of time. And then in 22 we had the RISAT 1A, and just few days back it was also used for a commercial launch for this. So this particular vehicle is considered as a very robust and highly reliable launch vehicle. And as a result of that, this particular technology is now being taken up by the industrial consortium of HAL and L&T, and they are going to start making 5 of the for the launch vehicles complete stage assemblies, and then subsequently they will start complete launch vehicle assembly and then launching in the country. And geosynchronous launch vehicles, starting initially with technology transfer from Russia. Of course, the geopolitical situation ensured that one superpower twisted hands of another superpower and ensured that you are not getting this technology. It paved the way for indigenous development. And today, with a large number of facilities established and conducting a large number of experiments, today we have more than one version of cryogenic engine operating and providing us the capability to put satellites into geostationary transfer orbit, and also enabling us to look at the human space program. We'll see some of them in the subsequent slides. So you can see in this that for doing all this, the requirement, as you also would be very familiar, that use of space technology, you need to make use of the industry, academic institution, and all possible resources for human capital, because you have the restrictions of the government coming into picture. And even in terms of the chips and then this fabrication, the foundry, the SCL CMOS foundry, the development, it was under a Department of Space for quite some time in the recent past. Now again, it's going back into the Department of IT. And in the period, we were able to use it for developing a large number of the instrument devices and also processors. And these processors have not only been flown, and they form the backbone for our launch vehicle Vikram processor. We have developed the CCD imaging sensors, and also the for SAR synthetic aperture radar processors have been developed. And another thing what has happened is software that have been developed and the geospatial platforms. In fact, feast one very interesting development, finite element analysis for structure and thermal, where collaborating with various other entities like BRC, NAL, and other CSIR entities also. This is being provided to the community in 3 versions, with an academic version, enterprise version, and an industry version, which is being marketed by industry. And every year a program is conducted where academic institutions add new modules to the capability of this phase, and developing such work and involving the various academic institutions. And in doing all this, a large number of industries have been made use of, and progressively this work is being hastened in a way in the recent past with the government's approach of bringing in space and then changing the policy and setting up, of course, the hypersonic wind tunnel facility, shock tunnel, which was established in Thiruvananthapuram, and a large number of the whole process of setting up pilot plants and making them work, and also developing miraging steel or multi-object tracking radar, which is also one of the important requirements for space situational awareness, where as space debris becomes more and more prevalent, keeping track of them and monitoring them becomes very important. And development of various materials, various new things have all been happening. And indigenization, of course, has always been one of the very key things, because a certain key material can become the showstoppers at times. So if you do not have more than one source available, so for that you need to make sure that you have your own capability. And while all this happened, the government also started looking at, as the Indian capability, not only in the Committee of Nations, but also its own economic strength increases, you cannot stay away from doing human space program. So initially it was tasking for before 75th independence anniversary, but then now because of COVID and also resources, program is slightly delayed. But then the idea is to carry our juggernauts into space and bring them back. And this particular activity brings in a huge amount of research activity in the country, both involving the academics and the industry, a large number of areas where the country is going to be benefited. And today, a large national collaboration with the different agencies are being done, and activities are all progressing in a systematic manner. And then just to give you a small brief on few of the things that have been done. Solid booster, again, human rating becomes very important. As you can visualize, if the machine or the equipment is not required for safety of life, the level of redundancy and the level of assurance you need to get could be one level different. And because of human rating, some new activities were required in all these areas, and these are going on systematically for making the booster as well as Vikas engine, which was what was being used regularly both for Mark 1, Mark 2 is being used. A large number of tests have already been completed, and using these also as an opportunity for conducting microgravity payloads and experiments. And in fact, what was mentioned during the introduction, how to make use of anything that is available. So we started looking at the spent stages of PSLV, which would have been orbiting in space as a debris. Instead of that, if you provide in that an ability to generate some power And if you can actually provide communication capability with that, you can use it for a large number of experiments. And in fact, these preliminary unmanned vehicles, which will be used for demonstration of safety and assurance, they also provide opportunity for doing some microgravity experiments, and those are also being planned as part of this. And today, validating the mission, conducting a large number of drop tests of the module, which will come back and land on ocean, those experiments, and then conducting the test vehicle development, model 1 and model 2. All these activities are going on, parachute deployment, and then dropping them. So in a nutshell, if you see what ISRO has been trying to do is making use of the leapfrogging as an approach. That means what is accessible to you in terms of technology, make use of it, and what is not accessible, develop them. And not only that, conceive of solutions to the problems you are facing in a manner which is cost effective and can work with the limited resources what the government make available to you. And in the process, demonstrate some things which are done very differently. So site was the starting point, and then between 95 and 99, in fact, India had the highest resolution imaging system operating in the civilian domain. And because of this, almost 18 ground stations across the globe were receiving data from these platforms. And then Mars orbiter mission, you are all aware that in the maiden attempt, a platform was put into the orbit of Mars. And then AstroSat, like I mentioned, it carries the highest angular resolution and sensitive instrument in the and also provides an observatory for our researchers, and then 104 satellites which was launched. So in this sense, if you see use of accessible technology and then conceptualizing them for addressing the societal problems and then demonstrating them has been the way things have been taken up and done. And if you look at in those aspects, the initial capability demonstration has happened, and now both in terms of the requirement as well as the need, what is required is capacity building and harnessing for the countries. We know that space economy is being talked about as currently reaching 400 billion and very soon reaching $1 trillion. And if India has to be a significant player in this, then the requirement has to different way of dealing with that is required. And that is where the government is looking at bringing in new policies and establishing a new platform. A platform like InSpace has been done, and that InSpace is what is actually being tasked with promoting use of space in the industry and in the startups, and then make use of all the facilities that are available across the centers within ISRO and also the technological capabilities that is there, and then move ahead and enable the country to really take advantage of the growth that has happened. So that, I thought, in a nutshell, is the journey of starting from the sounding rockets and reaching where we have reached today. And the whole country is moving in a very different perspective. Capability building is one aspect, but then capacity and using that capacity for not only immediate returns, but also ensuring that the country's economic growth also is benefited from this. So that's where we stand today. And at this time, I'll probably stop what I'm presenting, and I'm open for any questions that you might want to ask. Thank you very much for the patient hearing and also giving me an opportunity to talk to you about what has happened during these many decades. So this is an example of an image which can be taken of any part of the globe. We have a number of satellites operating with this kind of resolution. A 1 minute video can be collected across any part of the globe at a particular time of day, of course. Thank you. Thank you very much.
Thank you, sir. It was, I have no words to express my happiness seeing the kind of work done and the work that has touched the common man in every respect. A space view of what ISRO can do to the country. It's phenomenal, overwhelming in a sense. Now, may I request Ramanamurthy to take up some questions, please? If there are any.
Yeah, good afternoon. Good evening, rather. Professor Kiran Kumar, sir. This is Sanjay Malhotra from BRC, sir. Am I audible?
Yeah, please go ahead.
Sir, it's a large learning exercise listening to you from right from the sensors to the RF sources to the various developments. I have just for the powering the new thrust on the ion thruster. Do we is ISRO going for that? That is only one question, sir, because that will be involved. Plus the radioactive sources anyway you will be going, but ion thrusters is a new development, sir.
No, currently, in fact, we have already experimented use of plasma thrusters or argon ion thrusters, which are used in our GSAT-29 and earlier also in other satellite. And currently, of course, the capacity is very small. It's only few tens of millinewtons. But the advantage is when you operate it over a long period of time, it can provide the requisite thrust that is needed. Probably, as you are aware, today we are using it for doing what we call as station keeping maneuvers in the geostationary platforms. And this can also be used for actually moving when you are doing either from geostationary transfer orbit to the geostationary orbit during such periods. And of course, this extends the period of operation, but then it saves a lot of capacity and satellites requirement of power generation, because during the transfer orbit period, the payloads which are otherwise powered from solar power need not be operated. So that can be used for thrusting. But the point you're asking is, yes, ion thruster development is an important activity, and we are developing almost 300 millinewton and almost up to 900 millinewton type of thrusters are under development. And these are being done with our liquid propulsion center, both at Mandiyamala and at Bangalore center. They are working on this. And many of the components, including the cathodes, etc., are being indigenously developed for this.
Dr.
Thank you so much.
Yeah.
Thank you.
Dr. Manchanda has raised his hand. Parthaji, sir, we can go to you after Dr. Manchanda.
Sir, I am Manchanda, ex-BRC. It has been a wonderful talk. In fact, we are so proud of the achievements of the space program, particularly, all the societal activities of the government, they are being supported so well. My questions are two, in fact. One relates to the weather forecasting. See, I have spent some time abroad, and the precision with which the weather is forecasted is very high as compared to what we see in our whatever that IMD broadcast comes. In fact, it is anything but accurate. Even when they say monsoon will come on such and such date, so it goes off by weeks, not by days. Similarly, the temperature, in fact, abroad I have seen, even they tell so precisely the temperature, how it will fluctuate. Now, what are the challenges actually that are unique to our country? I'm sure that this must be a very matter of concern, so far as the space program is concerned and IMD, their interaction must be there for this. So please tell what are the challenges. That is number one. My second question relates to the GPS. The GPS that we are using now every day for our driving and for all other activities. So if I understand correctly, please correct me if I am wrong, that this data is coming from US agencies actually. So is it not a matter of security concern that we are allowing, these type of agencies to pinpoint, our all the locations in our country, and whether our own program can also be a substitute for the GPS which we are using actually. So I hope.
Yeah, sure.
Okay. Please
Yeah,
go.
sure. I'll try to answer to the best of my ability. See, one of the key aspect is probably, as you're aware, that even globally, weather forecasting using numerical weather models started improving significantly only when large amount of data over the oceans started becoming available. That means you have whatever models base make use of at the starting point. That means what you call as the initial condition. You give the initial conditions, and based on the skill of the model, it can propagate and tell what happens few hours later, few days later, etc., etc. So what is important is the input in the model itself. What is the data available for this forecast? So even globally, the weather forecasting made a significant saw a significant change when satellites started providing information about over the ocean, because 3/4 of the globe is ocean, and over that lot of data were not available prior to that. And with that data, the weather forecasting activity started improving significantly. Now, the other point is your ability to predict also depends on the model forecasting skill for certain regions. Like what they say is for temperate regions, when you talk about Western countries, America, Europe, etc., or higher non-tropical regions, when you take the number of variables which affect the weather forecast is significantly lower than what is required for tropical regions. So this is the second information. The third is, even in the numerical weather forecast model, apart from whatever data comes from the space, there are also large number of in situ observation on land, where, for example, you have a Doppler radar or other kinds of radar which are established. And these radars also provide inputs to the numerical weather model. So now if you look at the basics, that you have a model, and that model keeps improving with your past data analysis and the amount of inputs that you are putting into that. So your model is improving, but predictability depends on the number of variables that exist and your ability to provide inputs on those variables. So if you come to tropical region, it is not only India or IMD which has a problem, even globally also people are doing prediction over our regions. It is not that only IMD has a problem of predicting over India, even or in tropical region. Even weather forecasts of international agencies also have difficulty of predicting over Indian region. So this is now our improvements, whatever has happened, if you look at, for example, like I said, providing humidity and temperature profiles using whether it is infrared 3D data or humidity from our own microwave data, etc., when it's added. So it has brought to a certain level. But further improvements can happen if we are able to improve on the local, for example, Doppler radars, etc., and other radars on terrestrial. There the problem is again resources and the cost. So this is another aspect. The development that happens all the time, this is another. But now one other thing that is happening is even on land, when you want to provide such radars, the number of such things is limited. So there is a company which is now finding it commercially viable to have a constellation of microwave radars operating from space. It is attempting its first of the constellation later this year or early next year. They are planning about 18 or 20 satellite constellation to generate radar-based information over the entire globe and providing it as input to the numerical weather models. So these are the challenges of weather forecasting with respect to that, what is happening. So that part is, that is the one part. Second,
these private companies you are referring to Indian or they are global?
No, global, not Indian.
Okay. Okay. All right.
And here again, what you can see is those who can afford to build constellations and make are those who are ready to invest, wait for the results to come and success to occur. See, it's a huge risky business, and it's only those with deep pockets who will get into that. But today, if you look at globally, it has already crossed one level, And today, private companies are entering into space business and they are conducting space programs bigger than state or government run agencies. So they have reached already that level. Space is the real fourth frontier. And like human beings did over land, ocean, and air, now they are getting into space because you have the space tourism, space adventure, space exploitation. All this is happening. And it is this place which is actually providing. In fact, space companies are looking at setting up their own platforms for doing manufacturing, for providing the actually medicines being manufactured there. Today, already based on the experience which is available, some of the companies have gained billions of dollars with the kind of medicines they develop using the space station. So they are looking at independent of governments setting up space stations and running. So very soon what you are going to see is a proliferation of space economy in the private hands. That is why when the government is trying to enable more and more people, it is because the government itself cannot generate the kind of resources required for all these activities. It has its hands full for so many other things. But then technology doesn't wait for us to develop them and move ahead.
So second part of the second question, please.
Yeah, second part when you're asking, see today what happens is when you look at GPS itself, now it's a global system, whether it is American, Russian, or GLONASS or Beidou, they are operating over the globe and they are doing this transmission of these signals. So one of the things that is happening is anybody who is developing a ground receiver, he also does not want to depend on one system. So he is making his receiver work for capable of receiving signals from all of them and use them for developing his own positioning information. So the advantage is any one fellow deciding to stop, you can still make use of the others. And that is where, for example, why Americans also started giving the data available to general public, because they found commercial usage and commercial returns to the companies was so much more that they made it actually accessible to everybody. But still, there is a version which is high precision. There is a version which is generally accessible to public. And then what we did even in Gagan, for example, is in 26 ground stations across the country, you receive signals from all these GPS satellites, bring in corrections for clock errors and then ionospheric transmission errors. As you are aware, radio frequency when it transmits, moves in the atmosphere, produces some small delays in the depending on the weather, the presence of the various material in the atmosphere itself. But by determining accurately those information and sending it back to the satellite and broadcasting that information, which is received in the receiver on the ground. Along with this, if you process the data, your position accuracy comes to what is called as assured, we can say safety of life guaranteed. So actually the Airports Authority of India, after all this process, has assured Gagan receivers can be trusted for doing safety of life activity. That is how now aircraft which are registered in India after January of 2019 are compulsorily required to carry such receivers. And today, like I said, Indigo as well as SpiceJet have demonstrated that using these signals, they are able to land in ground in the airports which does not have the instrument landing capability. So these systems are coming into use. But coming back to your question, globally what is happening is commercial usage of this is forcing the governments to make this data accessible to everybody, though they might deny it for certain specific actions. Like when you are aware, during Kargil time, it was denied. And that's how the government also went ahead with our own Navik. And we, because of the constellation requirement, we went with 7 satellite constellation to cover India and 1500 kilometers beyond our borders. Though actual coverage is much more, but at least you are assured of this much region with your own source for doing various activity. So there is a general public use, there is a restricted use, and all these developments are going on. And notwithstanding that, you have receivers which are capable of getting all the data, process them, and then make use of it. And today we have also receivers which can make use of only NAVIC data and give you position accuracy to the tune of few centimeters. Also, these kinds of developments are happening. But then coming back to your prime question, whether you can depend or not depend, but today what is happening globally is drives or overrides everything else. And then the governance almost becomes subservient to what is available and accessible. How will people react to, you have seen, for example, whether you talk about internet or any of these social media thing, if sometime it is not available, people are almost making hue and cry. So if people get used to a service, governments are no longer in a position to tell you cannot use this. For example, China could stop the entire social media, have its own internet, have its own things. But in India, could such a thing be attempted? So these are the problems that are there in governance. So what the government is trying to do is its best, providing access in this its own manner and enabling Indian enterprise to bring in, whether it is broadcasting. So today, for example, the GSAT 24, which is being effectively hired by Tata Sky, that means they are assuring all the returns of that. That means service they are taking. So instead of government funding, launching and building the satellite, private companies will fund the building and actual use of that satellite. So the government expenditure on these satellites comes down. So whatever is commercially viable will happen through private enterprise. And then private enterprise can also provide service not only to India, to the global community, and earn returns from that. That is why when they say $400 billion economy, we are holding only 2% of that. We need to 10% or 20%. In all this, all these equipment, etc., is coming into picture, and more, the basic idea is make use of everything that is accessible, but make sure whatever instrument you are making can be relied upon even under worst case condition of somebody deciding to do mischief, etc.
Thank you.
Arshadi sir, you have.
Thank you very much, Dr. Kiran Kumar, for a very comprehensive and informative presentation. I have one suggestion that with the rapid development of space technology, do we have enough trained manpower? And what are the attempts by the government of India to introduce space science in the schools and colleges like that, so that we can get more trained manpower?
What you're saying is very correct. One of the very important aspects. And now a lot of work is going on. And while it had been happening earlier, but then again, resources was always a constraint. But now that the government is trying to bring in a lot of resources for this activity, providing space science and education through NCERT, and then bringing them through the syllabus at school level, and also bringing in courses at engineering and other academic institutions. This work is also now going on in a, you can say, a concerted manner. And InSpace is trying to engage with various IITs and other academic institutions to formulate programs which can be adopted in the engineering and other places for doing this activity.
Thank you.
Yeah, we'll take a question from Mr. Prasad and then Mr. Vaidya. Mr. Prasad, can you please unmute?
Good evening, sir. Talk covered a very wide spectrum of issues of space. This thing. Just I want to know policy for managing space pollution, especially end of life satellite management. Thank you.
Okay, so actually here also there are two aspects. One is initially when the launch vehicle itself, if say the spent stage, whatever material that is left, fuel, etc., is actually what you call as passivation. That passivation is done. And then the spent stage actually after a certain amount of time, it will re-enter the Earth's atmosphere and comes down. So those were being done in the launch vehicles. But now for future satellites itself, and you are also aware, the geostationary platform, when it was done to provide clear space in the 36,000 kilometer, all satellites were mandated to at the end of their functional life were asked to push the satellite into an higher orbit called graveyard orbit. So this was a actual operations plan, and that's how all the geostationary satellites are accounted. But now more and more, all the other low Earth orbit satellites also, it's not a, you can say, a legally bound activity, but more and more agencies are making it mandatory for people to keep in their satellites a capability to ensure that they bring it at the end of their operational life to an orbit where decay is very fast and it will enter the Earth's atmosphere and it will not remain in space for long. Of course, these are the intentions, and slowly it has to become operational requirement with agencies at UNO and UNOSA, as well as international astronomy associations, bringing working groups together. They are working on what kind of method should be adopted and what could be made mandatory through space policy and space law. So these are all currently processes which are going on, but there are as such no bound laws and regulations which exist as of now.
Mr. Vaidya.
Yeah, thank you. Dr. Kiran Kumar, you are doing a great service by giving lectures like this, because a lot of information comes into public. And my question is about the land titles being given by GPS system. What exactly is given in the hands of the property owner? Is it a drawing or a GPS marker? So what is that exactly? And how understandable is that?
Actually, your voice got little modulated. Can you just repeat once if you don't mind?
Yeah, I'll repeat. This is about the land title given using space technology. Land titles, property titles, or the map of the property or something.
Mr. Vaidya, hold your mic a little farther, little away.
Farther? Okay. Now is it okay? Better?
It's better, yeah. You hold it.
Better, okay, I'm sorry. Okay, this is about land titles issued to the property holders using space technology.
Okay.
What exactly is in the hands of the property holder? Is it a map? Is it a boundary? Is it a GPS marker? So what is it that you get in your hand?
Okay, so I'll just require a little bit of explanation for this. So one is the instrument itself will give you basically the position, latitude, longitude, height, and the time at which you got that information. That is all the basic instrument can provide. Now, using this, you need to do a lot of other activities. If you're talking about for a landholder, a cadastre, actually, that means drawing the boundary of a particular land holding, etc. So for that, what will be required is actually doing a sort of a survey using a relative. That means you have got one which is a stationary, which is known with a much higher accuracy, and then using differential GPS kind of observations, you can get your current position determined to few centimeter accuracy. And using that, you can actually generate the boundary of the area of interest. Or if you have got orthorectified images available, on that you can generate based on the specific position information, draw the boundaries of that, and using that create. But today, this is also supported in a way by actually generating much higher resolution images using drones, for example. When drones were not available, what was being done is that 30 centimeter or 50 centimeter accuracy images, taking them as the reference data set and using GPS or equivalent of that, generating this cadastral maps was what was being done. But now probably you are also aware that recently using these drone along with GPS and these whatever cadastral maps that were generated using geospatial information from satellite based, all of that is being further improved using drones for local regions, and that is what is being provided to the actual consumer through the agencies. I hope that answers the question.
Yeah, Ramarao, there are no further questions as of now. So shall we hand it back to you?
Yeah, it's already 6:30 plus. Malhotraji, can you?
Yeah, I'm ready.
Yeah, please.
Yeah, so thank you very much. Friends, I think all of you will agree with me that today's talk was not only it was so informative, but it really made us proud, made all of us proud for the achievements of Department of Space, who started their activities in 1960s with the sounding rockets. I think if I remember correctly, in 1963, Apache, one of the rockets was Apache, I think.
IK Apache.
Yeah. So, because that time it was under the Department of Atomic Energy. So with that, the journey started. And I think I very clearly remember when I was studying for my BSc, early 70s, I used to hear about this Aryabhatta and this happening. And I remember my conversations with my mother that, for example, in 1974, the Pokhran happened. So there was, the newspapers were flooded with reports about Pokhran. Whenever something related to space will happen, then the newspapers will be flooded with news about that. And as a child, I remember every time you hear one such thing, I used to tell my mother, I will go to this department and do this kind of work. Fortunately, I think somewhere it clicked and I could join BARC. But I think in one of those narrations, I had also declared to my mother that I'll be joining Department of Space and will be launching some rockets. Of course, I think that was not to happen. I was to be with BARC. So definitely, whenever we hear a success story of Department of Space, Dr. Kiran Kumar, I can assure you as an Indian, I feel it is my personal achievement. So thank you very much for a very, very lucid and very descriptive talk today you have given. And all the audience which is present here, and those, particularly those who asked very interesting questions to make the session more lively. I also thank, though he is in a not a very good condition, our president, Shri S.K. Mehta, and I also wish him very early recovery from his sickness. I'm told he is suffering of low sodium, so probably he gets well very soon, and we would like to see him active, not only on the platform of INS, but on the platform of his life as such. So wish him an early recovery, and thank him for his continued guidance. Even in his bad health today, he communicated and told us that he will not be there. So please take care of the webinar. So we appreciate that. I am also thankful of all my colleagues in the executive committee of INS, and particularly the webinar subcommittee, very ably headed by Dr. Ramarao, for conducting. So today, with today's this successful webinar, we can say we have done 24 of them. So today's was the 24th one. So now, as usual, I will be announcing the next webinar. So our 25th webinar, Silver Jubilee webinar, will be on 16th July at same time, evening 17 hours. And it will be delivered by Commodore Amit Rastogi, the Chairman and Managing Director of National Research and Development Council, NRDC, at New Delhi. And his topic will be IPR portfolio management in the context of R&D. So I think see you all on 16th July. Till then, have a wonderful time. Monsoon has very well come into India. So enjoy the beautiful season, and all the best, all of you. Thank you once again, all of you.
Thank you, sir. Thank you for
Thank you.
being with
Namaskar.
us. It was a pleasure. Thank you. Thank you very much.
Thank you, sir. Thank you for the.